Okay. Okay. All right. Where's my experiment? Okay. All right. When we left off yesterday, we had found complex roots to the red function. Okay? Now, the one thing I brought up in the morning class that I didn't bring up in the afternoon class is the interesting relationship between complex roots of any polynomial. So, tell me, what is the relation? This is two different complex roots, right? I got 3/4 plus root 47 over 4. And I also have what? 3/4 minus root 47 over 4. What are the relationship of those two? Morning people from yesterday can't answer. Afternoon people only. What is the relationship of those two roots to one another? I'll write them down so that you guys can see them. 3/4 plus root 47 over 4, and I'll put this in green, 3/4 minus root 47 over 4. What are the relationship of those two complex roots? Say again, Zach? No. Anybody else from the afternoon class yesterday got some insight on that? How would I say this? If I wrote you down, oh, I'm sorry. You know what I forgot here? Forgot my eyes. I forgot my eyes. Now does it help? Now does it help? I forgot my eyes. Now does anybody have any insight? Now that we have eyes, we can see it. Oh, that is funny. Oh. Say that again. They are complex conjugates of one another. They are complex conjugates. You're in the morning class. Oh, golly, Carter. Oh! All right, so here's a note. Here's a note, and we should have some insight on this just by looking at the quadratic formula. Is when we have complex roots in a polynomial, complex roots are always going to appear in conjugate pairs. Always. So, note, this is important, so afternoon people from yesterday, write this down. Morning people, we're almost ready for new stuff. Note, complex roots always. Should I put it in all caps too? Let's do all caps. Caps lock. Cursive. I just have to write. Always up here in, and we call these no, not conjuring, conjugating. Conjugating is a verb. You conjugate verbs, right? So conjugating means the act of conjugating verbs. All right, so the more you know. So write this in your notes, afternoon people. Afternoon people? You're not an afternoon person. That's right. That's right. So, complex roots always appear in conjugate pairs. Always, always, always. Now we're at the point, let me know when you're done writing, so I want that written on whatever it is you're writing on. Now, I want you to consider this function right here. I want you to consider this function. If I tell you this is a quartic, meaning what? Means order 4, right? Or degree 4 polynomial. Meaning that the highest exponent of x in that function is what? 4. Okay, good. We're getting our language down. I told you this is a quartic. Could you come up with a function that looks like this? Zach says yes, because why? Okay. I got a vertex. I got zeros. How many zeros do I have? 2. How many should a quartic have? 4. So how many complex zeros do I have? 2. 2 complex roots. How do I find those complex roots? Well, let me ask you this. We got a function here that is a quartic, but I got 2 complex roots. We're not to the point where we can find a function like this yet, but I can find part of the function. What part of the function can I find? The zeros, right? Based on the zeros. How would I do that? So I'm going to call my purple function here. This is purple in case you can't tell. I'm going to call that f of x. Okay? And that's going to equal, based on this 0, right, Logan? X plus 3, I'm putting in green because that 0 is in green. And then somebody other than Logan, what's my other 0 going to be? Ben, Bill, and Harleen. X minus 1, I'll put that in blue because that's blue and not purple. X minus 1. And then times something else, right? Times my other 2 that contain the complex roots, right? Let's call that g of x. Okay? And I'm going to define g of x as a, what degree polynomial do you think it'll be? Preston? Second degree polynomial. Why a second degree polynomial? Dawson, why second degree polynomial? Well, that's right here and here. So Morgan makes a good point. these two guys right here, when I multiply them together, I'm going to get something within x squared in it. Yes. Okay. Now, I take that something with an x squared. What do I have to multiply by? What type of polynomial do I have to multiply by to give me a quartic? Another x squared, right? Another quadratic. Good. So, I know g of x is going to be a second degree polynomial. And because all my real roots are addressed in this guy, this is going to be with what kind of roots? Complex roots. Okay, good. Now, let's see if I got my thingamajigger here. Yes, I do. Now, if I told you that this was Tyson, remember 2 and 1. Morgan, -5, 23, -21. Now, if I tell you f of x equals 2x to the 4th plus x cubed, not -25, -5, positive 23, -21. -5x squared plus 23x minus 21. If I told you this was your quartic, could I find the remaining complex roots? How would I do that? Can I factor this hot garbage? Nice and loud. Synthetic division. I love it. I love it. Why are you guys afraid of synthetic division? How do I do it? 2, 1, -5, 23, -21, right? And then I do my bizarro bar. And then what do I put up here? Do I want to do the green one first? All right, what do I put up here then? -3, very good. And then what do I do? I do this all right. Carry the 2 down. 2 times -3 is? -6. 1 minus 6 times -3 times -3 -30 times -3 21 and 0. Okay, now watch. Now I do the bizarro bar again. And I'll do that by positive 1. And then we'll do that in red, or no, we'll do that in black now. 2 times 1? -5 plus 2 times 1 times 1 and 0. So what is my remaining quadratic? So this, let's go back and do this in red, because now I know my g of x equals 2x squared minus 3x plus 7. Should I try and factor this?
No.
Why not, Henry? Why not? Can I factor something with complex roots? No! Why even try, right? I might as well just bang my head against the wall. I'm sure it does. I am sure it does. So, what do I do when I can't factor? Quadratic formula. So, x equals 3 plus or minus 9 minus 56 all over 4. Okay? And then what do I get? I get x equals 3/4 plus root 47 over 4, and I get 3/4 minus I almost forgot my eyes again, right? You're going to be my eye keeper, okay? 47 over 4 I. Okay? So, if we're given enough information, we can even find complex roots, right? Caleb, you okay? Tired or brain hurting? Good. 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 You know what the Marines say about pain? That's right. Pain is just weakness leaving the body. That's all it is. That's all it is. You want to see those t-shirts? Yeah, they do say that. It's like their motto. Makes you wonder why so many people join the Marines, huh? More pain! More pain! Oh. Hey, if you want to laugh, okay. Okay. What's that? There's a dude, okay, he does interviews on podcasts all the time. His name is David Goggins. Has anybody ever heard of him? He was a Navy SEAL, and after he retired from the Navy, he started doing like, I forget what they call them, but they're like 100-yard or 100-mile all-day races. No, they're like megathons or something like that. They're like marathons, except it's not even the Ironman. He's done that, but you run, basically, there's 2 requirements in order to complete the race. You have to run at least 100 miles, and you have to run at least 24 hours straight. And he's done that. What does he say he did? He did one of those races Saturday, rested 2 weeks, and then did one again 2 weeks later. The dude's nuts, right? But his whole overarching life philosophy is do stuff that sucks. Do stuff that you don't want to do, because it's not even physical training for him. It's mental training for him. It makes him mentally tough. And so there's an element of truth to that. Right, Caleb? Yeah. Pain is weakness leaving the body, metaphorically speaking. Okay? So, that is the lesson in a nutshell. That's it. So, what I want you to be able to do, okay, I want you to be able to, when I'm giving you a quadratic, you need to be able to find complex or real roots. Yes? When I'm giving you a cubic, you might have to find all the factors of that cubic. Okay? I'm giving you a quartic, and I'll give you 2 factors. How might I give you those factors? I might give you a quadratic and say x squared plus 2x minus 1 is a factor. That's not, no, plus 1. I might say that's a factor. Find the complex roots. Or I might give you a graph, right, of a quartic. And it does that. And I'll tell you where your intercepts are. And I'll ask you to find the quartic. Oh, I'm sorry, I'll ask you to find the remaining roots. So I'll give you the function. I'll tell you it looks like this, and you'll have to find the remaining roots. You know the two roots. You know the two real roots, right? What are the real roots? Here and here, right? How about this one? What are the real roots? How many are there? 4, right? Does this have any complex roots if it's a quartic? Okay. Trick question, right? Do we understand the relationship between intercepts, the x-intercepts, and our function? How are function factors? That's the big reveal on this unit, is the relationship between factors and how that function graphs and what it means for you. Okay? So that's what we're going to be doing for this section. And that really relates back to what we did in sections 2.2 and 2.3. Except we were dealing with nothing but real roots back then. Now we're dealing with complex roots as well. What's that? Ultra marathon. Okay. So you looked it up? All right. So, for your practice set, we're going to make this due on Monday, okay? Yeah. Monday. Tuesday. Shoot. How much time do we have left today? Yeah, half an hour. Okay. I got one more section to talk about. This is really easy. Okay? Check this out. The last section of the unit is rational functions. Okay? When I give you a rational function on the exam, I'm going to ask you to graph it. Okay? So, here's what I want you to think about. 3x plus 1 over 2x minus 3 equals f of x. What does that look like on the coordinate plane? Let me ask you this. What is the domain of that? Right? Why not? Makes what 0? My function can be 0, right? So my domain excludes any value of x that makes my denominator 0. You just want me to pathfind things. So, okay, now here's another little trick here. So, let me get my graph paper out on content. Fine. So, x and y. What should I do? You said my domain is x can't equal positive 3 halves. No. Halves. Okay. How do I express that on the graph? Vertical asymptote. Where? So let's do this. 1, 2, 3, 4, 5. -1, -2, -3, -4, -5. So positive 3 halves be right here, right? Okay, there's my asymptote. Okay? Now, I'll tell you this. What is my range? What is my range? Define range for me, Tyson. What does range mean?
Of the value of y.
All the possible outputs my function, right? What can't this equal? Let's do this. Let's do this. I want to build a table. X versus Y. All right? Let's start at x equals -5. When x equals -5, -14 over. So -14 over -13, so positive 14/13. Okay. How about, let's go with -2. 6, 7. 7 over 4, 1, right? Oh, wait. -6, -5. Thank you. -5 over -7. -5 over -7, so 5 7s. 0 is a good number, right? 1 over -3, so -1/3. How about 1? 4 over -1, so -4. Okay. What about 3 halves? Can't do that, right? Okay. How about 2? Should I dot these first? Let's dot them in red. So -5 is 14/13, so we might as well call that 1, right? So again, we're doing 1, 2, 3, 4, 5. 1, 2, 3, 4. Okay. So at -5 is 14/13. At -2, it was 5 7. So between a half and 1, right? So about right there. More than a half, but less than 1. At 0, it was -1/3. So about right there. At 1, it's -4. All the way down here. So what I'm doing here, I'll do this in a skinnier red, is doing like that. Okay? Now, how about over here on this side? Again, when x equals 2, let's rewrite this. 3x plus 1, 3x plus 1 over 2x minus 3. So when x equals 2, 6 plus 1 is 7 over 1, right? Positive 7. 4 At 4, I get 13 over 5, 13 fifths. So 2.5 almost, right? And then how about 5? Let's put 5 in there. 16 over 7. Okay, so now let's put those dots in. When x equals 2, it's positive 7, so it's way the heck up here, right? We'll call 7 like right there. 4, that's 3, that's 4. 4 is 13 fifths, which is between 2.5 and 3, right? Or we said 2.5, right? As an estimate, so about right there. And then 16 sevenths was 2. We're calling that 2, right? Because 16 eighths is 2 exactly. We'll just do that. All right? Now, thickness and form. Next, going to do that. Now, here's my question. Let's say I put 1,000,000 up here. I'll put 1,000,000 in for x. 3,000,001, right? Over, so 3,000,001, right? Over 1,999,997, right? What's that real close to? That's real close to 2 million. This is real close to 3 million. So what's it get to? 3 over 2, right? Will it ever equal 3 over 2? No. You'll get really close. What we call a math circle, we call arbitrarily close. It'll get arbitrarily close to 3/2, but it will never equal 3/2. How about on the, what's it? Yeah, but we're out of real life now. This is theory now. This is number theory. Okay? This is number theory. In this universe, y will never equal 3/2. At least on that side, right? On this side, as x goes zooming off to infinity, it will never equal 3/2. How about on the other side? Because it kind of looks like it's doing the same thing on the other side, going the other way, right? What if I put negative 1,000,000 in here? What if I put negative 1,000,000 in here? Negative what? 2,999,999, right? Over what? Negative 1,000,000 in there. So, what's the top real close to? Negative 3 million. What's the bottom real close to? Negative 2 million. So what's 3 million over 2 million? Or, I'm sorry, negative 3 million over negative 2 million? 3/2, right? Will it ever equal 3/2? No. So where can I put a horizontal asymptote? At 3/2. So then I do this. Oh, my graph's off. My graph's off. So, riddle me this. Should I draw my asymptotes in before I draw my graph?
Yes.
Yes. How did I get 3/2? How do I get 3/2 just by looking at this? these become more and more meaningless as x zooms off into infinity, right? The 1 over here and the 3 over here, they become more and more meaningless as x gets higher and higher on the right-hand side, or lower and lower on the left-hand side, right? Okay. So, when I'm figuring out where to put my horizontal asymptote, I ignore these guys and just look at my coefficients over here. So, anybody notice a coincidence here? Where's my horizontal asymptote? Where's my vertical asymptote? Is that a thing, or is that a coincidence? It's a coincidence. It's a coincidence. I'll prove it to you. 6x plus 1 over 5x minus 1. What's your domain? One bit, right? And what's my range? You were thinking the answer to this question, Tyson. 6 fifths. Y can't equal 6 fifths. So then what I would do when I ask you to graph it, I'd put in my asymptotes. So I put one in at 1/5. One, 2, 3, 4, 5. This is 1. This is 2. All right, and then 1, 2, 3, 4, 5. This is 1. This is 2. This is 1. This is 2. And then I put a vertical asymptote where? Oh wait, I screwed up. You guys screwed. What did I screw up? Yeah, this should be a vertical asymptote, right? There. And where should I put my horizontal asymptote? 6 fifths. So right here. Right there. Okay, now what do I need to do? Let me ask you this. What's the easiest number to plug into this? 0. 6 times 0 is 0, plus 1 is 1. 5 times 0 is minus 1 is positive 1 divided by negative 1 is. So when x equals 0, y equals, which is down here. When x equals 0, y equals negative 1. Now, I say I know how this behaves. Remember, it's in this quadrant right now. And I don't mean this quadrant as in the Cartesian plane. I mean this quadrant with respect to my asymptotes. Right? And it does this. It goes, and then where's the other one? It's an odd function, right? Kinda. And you graph a rational function. Why do you think they call it a rational function? Why do you think they call it a rational function? Look in the word. Yeah. MREs. Ratio. No, we don't. We eat well on submarine. You know why? It's the only way to prevent mutinies. Because submarines really suck. But if you don't have good food on a submarine, you're going to be a very unhappy person. All right? We're going to work more on this on Tuesday, okay? I'm going to assign the problem set for lesson 2.4. I want that due on Tuesday. Yes, sir.
Are we going to train this in, or are we just going to show it to you?
We're going to show it. I like showing, right? But here's a couple things. When you show it to me, I don't want you guys to try and save the rainforest. Okay, what do I mean by that?
Show your work.
Show your work. When in doubt, use more space to show your work, okay? We're not trying to economize on paper, okay? Do you think you're going to save a tree by crunching all your answers on one piece of paper?
Yes.
Over time. You might save one tree in your entire life. And that's if you're doing math your entire life. Okay? Now, there's that. But, how do we really make a dent in saving the rainforest, let's say, or anything else? We learn new and creative ways to solve problems. And this is one of the best tools that we've come up with as the human race to figure out ways to solve problems, okay? So I want to see your work. I want to see your reasoning. You're not going to save a tree by making yourself on one piece of paper, okay? So, section 2.5 on. Section 2.5, problems are, I'm sorry. Yeah, 2.5. That's why. All right. Yep. This is on page 144. Okay. What's that? We did 2.4 already. All right. I know. All right. So, 9 through no vocab. Okay, that's it. That's it. Now, those of you with graphing calculators, use your graphing calculators. Okay? Those of you without, use Desmos. Why do you need a graphing utility? To see the graph. I'm sorry? Yes. Well, it's the nice thing about Wabbit Emo or whatever it's called. That's what I got down here. I got it right there. So, hey guys, who's bummed over the fact that they don't have a graphing calculator? Do you want a solution to that without paying $120? Download Wabbit EMU. Wabbit EMU. It's a what we call graphing calculator emulator. It emulates a graphing calculator, meaning you enter stuff on it just like you would the graphing utility or the graphing calculator that you see at Walmart for $80,000. What's that? You do, but this will give you practice on it while you're waiting to buy one. Okay? I would call it you may use Desmos as well. The only drawback with Desmos is you can't use it on a test.
Yeah.
Then you can't use Wabadoo on this either on the ACT. But the nice thing about Wabadoo, it's awesome.
Yeah.
Look at me. Wabadoo. It's awesome.
Yeah.
Look at me. Look at me. Wabadoo.